Welcome back to another lecture series. Now in today's video we're going to be talking about refraction. Okay, we're not just going to be looking at refraction, but in particular we're going to be talking about refraction through a triangular glass prism. Now here is a triangular glass prism on the board. Okay, so we're going to see the equation and everything that has to do with refraction through this prism. Okay, now the first thing we're going to do is pass light through this prism. Okay, now I could do it in different ways. I could pass it through this end to this end. This end, it doesn't really matter. Now let's say we're having a triangular glass prism having an apex angle. Apex simply means the top or highest point. Okay, so we're having an apex angle, which is the top angle. We're going to call it A. Now if I should pass light through this prism in this form, okay, now the light ray, which is the incident ray, is going into the light prism from this left hand side of the diagram. Now what's going to happen? The first thing that usually happens is we're going to observe a normal. Okay, a normal is simply a line that separates the incident ray and the plane. Okay, it helps us indicate or identify the incident and the refracted or reflected rays. Now we just pass light into this prism. What's going to happen? Now remember we're talking about refraction. Okay, now remember that refraction is the bending of light as it moves through different layers, okay, of different optical densities. Okay, so what happens is, since we're passing it from air, okay, we're going to assume that the surrounding around this glass is air. We're going to pass it from air into this glass prism, of which we do know that a glass prism is optically denser than air. Okay, it has a higher density, which means that it has a higher refractive index. Now as we pass it through this prism, we're going to observe a normal. Now what happens is the light ray isn't going to go through, okay, straight. No, because it's passing through different layers which are having different densities, okay, or refractive index. So what's going to happen, remember, as it's moving from a medium of less density to that of high density, it is going to bend. Okay, so we're going to have the light ray bend like this. Okay, I'm going to indicate it using outlines to show you that, okay, the light is actually passing from this point down to this point. Okay, now as it forms a normal, first of all let's indicate the incident angle, which is I1. Okay, I'm going to call it I1 for a reason, you see it soon. Now I1 is the incidence angle as the light ray moves from air down to the glass prism. Okay, so as it strikes this air and glass layer, it bends through the prism. Now what's going to happen as it tries to emerge from this other end? Remember, it's now moving from an optically denser medium to an optically less dense medium. What happens again is that it bends away. Okay, it bends away, and remember, as it bends, we're also going to have another normal. Okay, let me indicate the normal with a straight line. We're also going to have another normal. Now just the same way, if I should pass the light from here, I'm going to get the same thing at this end. So if I'm having an incidence angle I1, imagine I'm passing it from this point, I'm also going to have an incidence angle which I'm going to call I2. Okay, I'm going to have an incidence angle which I'm going to call I2. Now how about the refracted angles for each side of the prism? Now remember, refraction or the refracted angle is the angle between the refracted ray and the normal. Now here lies the normal, it doesn't change, and here is the refracted ray, okay, the ray that is passing through the prism. Now the angle between the normal and the refracted ray, I'm going to call that R1, and then I'll come here, the angle between here is the refracted ray. Okay, the refracted ray remains the same if we're coming from here, and here is the normal. I'm going to call this let's say R2. Okay, now this is going to be R2. Let's try and extend these lines and see what we're going to get. Okay, if I extend these lines, here's what I'm going to get. Now it doesn't really matter if this one comes out of the triangle or not, or I might also want to extend it and see, okay, and show you guys what we're actually going to have. So if I increase the scale of the triangle, I'm going to get something like this. Okay, now I'm just changing it just so that everything can line inside of it. It doesn't really matter if I choose to bring it out, nothing changes. Okay, all the mathematical principles and theorems are going to apply, it still remains the same, nothing is really changing. So we're having R1 and R2. Now we're having something like a V shape here. Okay, there's a reason for this as well. This because I plan on applying some mathematical principles or geometry just so that we could get some mathematical formulas that will be applied to this triangle. Now, how about if this ray, this light ray, was allowed to pass through this point? Okay, now I'm going to call these rays I'm passing through this point the weak reflected rays. Okay, so assuming it's passing through weak refracted rays, rather, assuming it is passing through, we're supposed to have something like this. Okay, and also assuming it is passing through, we're supposed to have something like this. Now take note, the angles formed by the two weak refracted rays, okay, the two weak refracted rays, I'm going to call it the deviation. Okay, I'm going to call it the deviation. This angle is going to be called what now? The deviation. Now I'm going to pause that for now. Now watch again. You notice from geometry, we do know that when we sum the two opposite interior angles, okay, it is always equal to the opposite exterior angle, okay, for any polygon. So when I sum R1 and R2, what I should be getting is R1 plus R2. Now I'm going to call this equal to R. So I'm going to come here and write R1 plus R2. I'm going to call it what now? R. Okay, just so that I can get rid of this R1, R2. I'm representing the sum of them as R. Okay, now what other thing can we derive from this triangle? Now, the next thing we're going to take note of is that assuming I was passing this incident light ray directly through this prism in this form, I'm going to have the incident light ray to be perpendicular to the normal, okay, to the plane rather, just the same way we're having the normal like this, perpendicular. If I should pass it like this, we're going to get an angle here, which is 90 degrees. Now, what if I now choose to increase that angle as I tilt the incident ray downward? Now, once I start bringing this incident, let's assume this is the incident ray, it's here, and once I start increasing it down this part, okay, it's going to be increasing. Now, what do you think is going to happen to the minimum deviation, or deviation rather, not minimum deviation? Yes, okay. I would like you guys to pause the video and think about it. Okay, if you thought about it, let me know in the comment section, or if you did, there's still no issue. Now, let's see what will happen to this guy as we tilt the angle of incidence, or increasing the angle of incidence. Now notice, as we are increasing the angle of incidence, what happens to this angle is that it will get smaller, this deviation. Okay, it gets small up to a point, okay, where it will have its smallest value, and the point where it's going to have its smallest value, as at that point, this incident ray would have been lying side on this glass prism. Okay, now as at the point where this guy is going to be its smallest value, it is when this ray is not lying on this prism like this. Okay, that's the point. Now that point, we're going to say this guy is what now? Having its minimum value. That's why at this point it's called the minimum deviation. I'm going to indicate this as well. Okay, so this is called the minimum deviation. Okay, that's called the minimum deviation for the angle. Now, what else can we take note of? We do know that from Snell's law, okay, refractive index is equal to sine the angle of incidence. I'm going to call this I1, okay, divided by sine the angle of refraction, that's sine R1, okay, and this is equally equal to, we're going to have sine I2 divided by sine R2. So basically, we can make use of any of this, okay? They are actually the same thing, okay? Actually the same thing. Now, another thing we want to take note of, okay? We want to take note that the angle here, okay? The angle here, which is R, is equal to this angle divided by 2. We're going to prove it and see how it's actually true, okay? The angle here, which is R, is the apex angle A divided by 2. Now, how is that possible? Just like we said, R1 plus R2 is equal to the exterior angle here. Okay, equal to the exterior angle. Now, if you notice, this diagram is kind of symmetrical. If light ray comes here, it passes through it emerges here. Okay, if it comes here, it passes through and emerges here. So since both sides are symmetrical, R1 and R2 are equal, I1 and I2 are equal. So I'm going to write and say, since the prism is symmetrical, okay, then we have R1 to equal R2, okay, and I1 to equal I2. Therefore, we're going to say refractive angle, okay, at the first interface equals the refractive angle at the second interface, as well as the incidence angle at the first interface equals the incidence angle at the second interface. Okay, so if I come here and say R1 equals R2, I can represent them as just R. Okay, so if I sum R1 and R2, if I sum R1 plus R2, okay, or I can choose to eliminate this R first. Okay, if I sum R1 and R2 and I say, okay, let's both of them equal R, I'm going to have R plus R. Okay, now R plus R gives us what now? 2R. So instead of having R here, I'm going to write this as 2R if one of them is equal to R, or both are equal to R. What I'm trying to say is that this angle has been proven to be R1 plus R2 from the geometry illustration I gave at the beginning. Okay, R1 plus R2, that's what we're going to have here. Now, since we've seen that R1 and R2 are equal, if I say let R1 be equal to R and R2 is equal to R as well, since they're already equal, so R plus R, what do you get? You get 2R. Okay, now that 2R is also having here. And then again, the angle here from geometry, okay, opposite interior angle, or rather interior angle is equal to opposite exterior angle. Now interior angle is the angle inside. We're having a shape like this, okay, a quadrilateral. The angle inside is equal to the opposite, this one is opposite, but exterior outside is equal to the opposite exterior angle. So we can as well see that A, which is the apex angle, is equal to 2 times R, of which R is equal to A over 2. This is something we just proved, okay, like I said initially. Now, it doesn't stop there. We also want to continue and see what we're going to get. Now, you can see that R1 is equal to R, do not forget, or we can say R2 is equal to R. So they are basically the same thing. I could as well say R1 equals R2 equals R equals A over 2. Okay, that's quite important. Now, how about bringing the minimum deviation into the equation? Okay, how do we do that? Okay, let's see what we're going to do. Now, applying the principles of mathematics or geometry again, I1 and this R1, okay, we do know that applying the same rule, if I can get two angles in here, I can sum them up to give me the minimum deviation, isn't it? Now, I can actually sum two angles, okay, inside of this place to get what now? A minimum deviation. Now, how do I plan on doing that? First of all, I'll have to find this angle and this angle as well. Now, we can still find the angle. There is no problem with that. Notice that we're having a normal here, which is a straight line, and then we're having the incidence ray and the assumed refracted ray, okay, if it took that part. So we're going to have a straight line like this and a straight line. Now, when two lines cross each other in geometry, the angle under it equals the angle on top, the angle at the side equals the angle at the side. So we have what we call the vertically opposite angles, okay? So we're going to have what we call the vertically opposite angle. Okay, I'm going to use another marker and indicate what I'm trying to say. Okay, so this is called the vertically opposite angle because this one is opposite to this and this one is opposite to this. Okay, so that's the vertically opposite angle. Now you notice we're having another straight line here, another straight line here. That's an X shape. Okay, so all the angles formed here is same as the angle formed here. Okay, so it means when I add the angle here and the angle here, I'm going to get I1. Okay, I don't want to give name to this angle. Okay, I don't want to introduce in any new expression, but you notice when I add the angle here and the angle here, I'm going to get I1. That means the angle here is simply when we subtract R1 from I1. So I'm going to put it in brackets. The angle here is I1 minus R1. Okay, that's quite easy. I'll go over it again. Vertically opposite angle. Okay, here is a vertically opposite angle. This is an X shape. Okay, between these four lines like this. Okay, now vertically opposite angle simply means when two lines intersect, the angle formed on one side equals the angle formed on the opposite side. So the angle here is same as the angle in all of these parts. So when I add all the angles here, I'm going to get the angle here. It simply means since this part is into 2, if I want to get this one, all I have to do is subtract R1 from I1. That gives me I1 minus R1. Okay, now I'll do the same thing here. Now for this guy, we're having I2 and we're having R2. Now here is the vertically opposite angle. We're having the normal, which is straight, and then we're having another incidence ray, which is what now assumed to be straight. Okay, that's the emergent ray actually, but since we can come from both sides, we're going to call it the same name as the incidence ray. Okay, so for the same thing, to get the angle here, I have to subtract R2 from I2. So I'm going to have I2 minus R2. That gives us the angle there. Now what do you notice? Same principle applies. R1 plus R2 gives us the angle here, which means when I add these two, I'm going to get the minimum deviated angle. Okay, that simply means that the minimum deviated angle equals I1 minus R1 plus I2 minus R2. Okay, now that's going to be equal to I1 plus, okay, let's bring it together, plus I2, okay, minus R1 minus R2. Now if you recall, we did say that I1 and I2, they are equal, so I can replace I2 with I1. Okay, so if I do that, I'm going to get I1 plus I1, that's 2I1, okay, minus R1 minus R2. R2 is same as what now? R1 or R, okay, it doesn't really matter. So if I do that, I'm going to get, let's say, minus 2R1. That's what I'm going to get, because minus R1 minus R1 is going to give us minus 2R1. I could choose to use these two as well. It doesn't really matter, okay? Now, here's what I'm going to get. And then we can say the minimum deviation is 2I1 minus 2R1, okay? And we can also factorize 2, giving us minimum deviation over 2 equals I1 minus 2, or rather we could decide to make I1 the subject. Okay, if I choose to make I1 subject, I'm going to get I1 is equal to, now the reason I'm making I1 subject inside is because I want to substitute into this equation. Okay, so I have to make I1 the subject. So if I make I1 the subject, I'm going to get minimum deviation, okay, plus 2R1 divided by 2. Okay, I could as well separate it to give us I1 equals minimum deviation over 2 plus R1. Now R1 is basically equal to R2 and is basically equal to R. So I can switch to substitute. Therefore, I'm going to get I1 equals minimum deviation over 2 plus, I'm just going to write R. Okay, this formula first of all connects the incident angle, okay, minimum deviation, and the refracted what now? Angle. Okay, so in this case, I'm not having R1 or R2, I'm having just R. And here, I can be written as just I1 or I2 or even I. Okay, I think it's as simple like that. So I can even choose to eliminate the 1 there, because I remains the same for both sides. I1 and I2 equal what now? I. Okay, I would as well write it here. I1 and I2 are going to equal what now? I. Now that is the incidence angle. How about the refracted angle, which is R1? Now we already proved that R1 is R2 and R, and it's also equal to A over 2. I'm going to substitute this and this as well into this equation. Then we're going to get a general formula for solving the refractive index when we are given the minimum deviation, refracted angle, and the apex angle as well. So I'm going to say refractive index, okay, equals sine the angle of incidence. And what's the angle of incidence in this case? The angle of incidence is minimum deviation over 2 plus refracted angle, okay, divided by sine, okay, what's now the refracted angle? Now, our advice is that you shouldn't go and make our subject formula to make it complex, okay, and you'll be having the same thing. You might still not be able to solve. So what you might want to do is substitute for A over 2 as well. So we're going to be having sine A over 2, okay, and this gives us the general formula for calculating refracted angle of incidence, okay, which is I, using this formula, or the apex angle, or in general what connects everything. We're having the refractive index in this case. Okay, so the refractive index equals to sine minimum deviation over 2 plus r blah blah blah, just exactly what you're seeing on the board. Okay, now I think this video gives you a basic understanding on when light passes through a triangular prism and what happens. Okay, now instead of cramming these formulas and every other thing we're having here, if you can't cram them, all you have to do is understand this procedure. And if you're given a question like this, first things first, draw the triangle, and then what are we going to have? We're going to have the various parameters inside of it. Understand the concepts on how we're going to get the minimum deviation if we choose to pass it directly through the prism, making an angle of 90 degrees, which makes it orthogonal or perpendicular. Okay, and then increasing the angle, noticing that experimentally, okay, mathematically we could not prove that this one tends to decrease. Okay, it can only be proven experimentally. Okay, so when we start increasing the angle, what happens is that minimum deviation tends to occur. That is, the deviation angle tends to start what now reducing, giving us the smallest possible value for this d. Okay, now here is a quick review on refraction through a triangular prism, and I would like you guys to go through the video, and we'll have other videos as well for other courses that you might also want to check out, okay, for your physics, depending on any exam you're writing, whether WAEC, O level, JAMB, UTME, post-UTME, 100 level, and even down to 200 level as well. I do hope that this video will be quite useful for any student that is taking a physics examination. Okay, and do not forget to like and follow Dr. Flash on YouTube. Also, do it to click on the notification bell so that when a new video comes out, you'll be one of the first persons that get notified. Okay, and you don't miss any of this. Also, you might want to share to your friends, and if you do not want to learn alone. Okay, see you in the next video. Stay tuned.